again. Today, the last day about partition trees. Maybe I'll take a little bit less time than the previous 2 days, but we'll see. Maybe we can get some more time. So, what I want to talk about today is, so far were either structures that had used a lot of storage and squared maybe in 2D or x to the power of 3 in 3D, but then had very good query time. Okay. Or they had the storage was very good, linear. These two things. And I also want to go through it's an example of how to use things with this trade-off, go through two applications. So, like I said, what did we do so far? First day, we looked at partition trees, linear storage, and to the 1/2 plus epsilon query time, cutting trees, and squared storage log n query time. So in the second day, yesterday we looked at multi-level structures, and before I go to trade-offs, I want to explain a little bit about how you can improve one of those things with a very easy trick, and that's this one, this cutting tree. Okay, it has n to the 2 plus epsilon storage, and if you have t levels, then this t minus 1 should also be t. It has log to the power t query time. Right, so if you two levels, you get a log from the first level, and then for each of the nodes on the first level, you have to search in the second level. And so, let me, for instance, as an example, we looked at this line segment intersection. Okay, so now I can express the fact that a segment is intersecting my query line as one endpoint should be below, the other endpoint should be above. So I have a two-level tree where the first level selects all the segments where, let's say, the left endpoint is below, and the second level selects all segments where the second endpoint is above, the right endpoint is above. Okay, then in the query algorithm, you search with a line. So in the partition tree, you would say, okay, these two triangles are completely below the line. So that means that their left endpoints are below the line. So if I want to find the segments intersecting the line, then out of those I should find the ones where the other endpoint is above. And for that, I had this second partition tree on the right endpoints, and here I can just do a query to find those on this second level trees. Okay, I hope you remember that for the cutting trees it worked in the same way. So here, suppose I have, in my cutting, I have a collection of triangles, okay, and so on. And let's look at this triangle. Okay. We have a number of lines that pass through the triangle, and I had these lines that, I don't have a red one, that go above the triangle. Okay? If the query was here, and I want to report everything above this point, well, then in my tree, let's say I go to the root, I check all these triangles. Let's say my query point Q is inside this triangle delta I. Then I go to this corresponding node WI. And, well, if I want to count the number of lines above, I simply add this number and I recurse. Okay? For a two-level tree, here I had another structure, okay, and now I have to search here, and then I also go in recursion in this tree. Okay, so what happens is I'm going to go down a path in this tree, and for every node on the path I'm going to go to my second level structure and do another query. Okay, since I have log n nodes here, and in each of these second level trees I also do log n work, I get log squared n. Okay, now there's a very nice and actually easy trick to get rid of this. So how does anyone have any idea how you may want to try to do it? So the problem is that here I have log n levels. For each level I spend log n time. So if in this main tree I could have less than log n levels, then, well, let's say a constant number of levels, then I only have a constant time this log n. Okay, so the idea is to try to reduce the number of levels. So what do I have to do to get a smaller number of levels? Well, if you look at the tree, so let's first look at the binary tree, where here I have two subtrees, let's say of size exactly n over 2. Okay, now what is the depth of the tree? It's going to be log base 2 of n. Okay, if I would have three, what's the depth? Base 3, so it becomes a little bit smaller. Okay, so what we were doing is we actually have, well, lots of these things where each of them, well, actually was at most 2n divided by r. No, sorry, here it's just n divided by r. Okay? So I get log base r. So now I would like to make this r, the bigger I make r, the fewer levels I will have. Okay? Of course, as long as I pick r a constant, right, then this is simply going to be something like log base 2 of n divided by log base 2 of r. Okay, so indeed, if I make r larger, it gets smaller. But when r is a constant, this is still going to be order log n. So what I want to do is I want to make r not constant, but dependent on n. Okay, so what I'm going to do is, where is my, here. I'm going to say, okay, how am I going to pick my r? Pick r equal to n to the power epsilon. Or actually, when I go into recursion, my n gets smaller. So this, what I'm actually going to take, well, let's call it n0, so the original number of lines. So this r is not going to get smaller when we go down the tree. It's always going to be the same value, namely this n, the original n to the power epsilon. So how much is the depth of the tree going to be? Well, so initially I start with n, or n0, then I go to n divided by n to the power epsilon, then I go to n to the power, well, n divided by n to the 2 epsilon, and so on. Until I'm at size 1. So how many steps do I have to take? Yeah. 1 over epsilon, right? Because here at the end I have something like, okay, after k steps I have n divided by n to the k times epsilon. So if I take k 1 over epsilon, then this is simply n divided by n is 1. Okay, so the idea is very simple. Simply pick, instead of r a constant, I'm going to pick this value. Okay. And now, in here, this is going to be O of 1, or maybe 1 over epsilon if you want, but epsilon is a constant. Okay, so this is simply O of 1. And I get this. Okay? So actually I'm forgetting one thing here, or I'm cheating a little bit, because what do I have to do? So where I'm not cheating is, okay, I go down the tree, the number of levels is a constant, 1 over epsilon. For each of those nodes I do something here which takes log n time, so that's this. But actually, what do I have to do at this node? I have to decide whether I have to go here, 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 or here. Right, so how did we do that before? Well, I simply said, okay, I have here I have how many nodes did we have? R squared, right? O of R squared children. So I said, well, R is a constant, so just check each of the children whether you have to go to that node. But now R is not a constant anymore. So if I'm going to check all of them, and I have n to the power epsilon children, then I spend n to the power 2 epsilon time. So what I win by having only a constant number of levels is completely gone because of this. Right? Or maybe stated or written in a more precise form. So our recurrence for the query time was something like, check each of the children or each of the triangles in the cutting to find where you have to recurse, and then you get this. Okay. Now, by picking a large R, plus a log n to go to the second level data structure. Okay. Now, by picking R very large, that's good for this term, because now this R is large, so the size decreases more rapidly, and I get only log n levels. But picking a large R is bad for this term. And if I already put n to the 2 epsilon here, because I have this many children and this is my value of R, then, well, the solution is going to be n to the power 2 epsilon or something, which is worse than log n. So, how can I avoid this? Well, why did I need this time here? Exactly. So I need this much time because I had my cutting. And I needed to decide for my query point in which triangle it lies, because then I know at which node to go to. So instead of simply checking each of these triangles one by one, which is fine if you have a constant number of them, I build a point location structure on this thing. Okay, so point location. So what happens to this term? Well, how much time does point location take? Log n, right? And here n is actually r squared. So I get log of r squared, which is asymptotically the same as log r. Okay? So now my recurrence is q of n is, well, together this is log n plus q2n over r. And now in this large r, you have a constant number of levels and you get log n. Okay, so using this trick you can get the query time from log squared n to log n, and actually if you have 3 levels, 4 levels, you can always do the same thing and the query time stays log n.
Can't we use this idea for the data structure of higher levels?
Yes. Yes. But it's a little bit more tricky in the sense that you need this point location data structure. Okay, so in 2 dimensions, we know if you have a planar map, let's say of size r squared, or well, let's say of size n, then we can have a point location data structure that uses linear space and has log n query time. So in higher dimension, such a structure does not exist. And to get log n query time for point location in high dimensions, you would need more than linear space, something like n to the power d. But because the size of this structure is, well, n to the 2 epsilon, that sort of also always disappears in this epsilon. So you can use it in high dimensions as well.
Doesn't this trick increase the size of the space that we have to use? Because in each node we have to make a point location database, and so you have to decrease your...
It increases the storage, but only by a constant factor. Because, so for each node, well, for each of the children, you already stored that triangle anyway. Right? So you use R squared storage to store all the triangles. Now, in addition to that, you have a point location structure, which also uses, well, linear space in the number of triangles that you have. So you need an extra O of R squared space, but you needed that anyway, so it doesn't increase the asymptotic bounds.
But here R is depends on N. It's not, R is not constant anymore.
No, that's true, but that doesn't matter. So what happens for the storage? Okay, I get storage is O of R squared, plus O of R squared, S n divided by R. And this solves to n to the 2 plus epsilon also when R is n to the power epsilon.
When we use point location, we need to report the triangles, right?
So when you do point location, you have the cutting, so it's a collection of triangles. And the point location structure will, if you have a query point, it will report the triangle containing that point.
Yeah, so it should be log n plus k, the number of...
No, because this is these triangles form a subdivision of the plane. So that means that there's only one triangle, there's exactly one triangle containing this point. So this plus k, I mean k equals 1. My cutting in the simplicial partition, that could look like this, right? With lots of points in here. And then you would have a problem. But here, it's disjoint and you don't have the problem.
Sorry, how do we end the partition tree in this structure? It's just like a level in multi-level cutting tree, or we should have a specific kind of structure for having the point location structure. We have multi-level cutting tree, yeah?
Yeah.
One specific level defines the structure for point location, yeah? Or
so if you have, so basically for every node in the first level tree, and if you want to do it for multiple level, also for every node in the second level and in the third level and so on, only in the last level you don't need this. For every level, for every node in each of these levels, you're going to have a point location data structure. So if I draw the picture of the tree again, okay, so so it used to be that, let's say, in a 2-level structure, well, each of these things had some second level tree. But now all of them have a second associated structure, you could say, which is for point location. And this is also going to have a second thing for point location. So each of these is now going to have two things. Okay, so that let's say when you go here, you do, well, as usual, you'll query on the second level tree, and then you do a point location so that you can decide where you have to go down. Okay, so this is maybe if at some point you can also sometimes use it in some other data structures. If you have something with multiple levels, then this trick of picking R, not a constant, sometimes can help a little bit.
If you can achieve roughly constant time in one level tree, can't we achieve all t time in a t level tree?
Okay, so
we need to have the data structures beforehand because
yeah. So, but the why this doesn't work is that in a one-level tree, this doesn't help because let me write the recurrence again. Okay. So this is for a two-level tree, right? Where, well, we go into recursion, but we also have this term for searching in the second level tree. If you have a one-level tree, then this is no longer there. Okay? Of course, in a one-level tree, I still get a constant number of levels, but this here was now going to be log of n to the, well, actually L squared is log n. Okay, so now this will be the dominating term, and you don't gain anything. You have fewer levels, but at every level you now need to do this point location, which is going to take you more time. Okay, so this was a little bit tricky, but the good news is we don't need this for the rest of the lecture today. So even if you were a little bit confused, you should still be able to follow the rest of the lecture. So, as I said, what I want to do today is look at this trade-off between query time and storage. And let me motivate this by, well, an application or a well-known problem in computational geometry that maybe some of you know. Does the name ring a bell? No? Okay, so this is a famous problem, not so much because it's very useful, but because it's, let's say from a theoretical point of view, it's a very interesting problem to see how fast you can solve it. And the problem is the following. I give you a set of n points and a set of n lines. Okay, so it's not a query problem. You just have a set of n points and n lines. And the only thing you want to know is there a point that lies on a line? Okay, so at least one point lying on at least one line. So in this case, the answer is yes, because I have this point on this line. But if this point would not be there, then the answer would be no, because all the points, none of the point lies on any of the lines. So, and the big question is, how quickly can we do this? So how would you solve it? Well, you can do a plain sweep. what will be the running time if you do a plane sweep? N squared log n, right? Because when you do the plane sweep, at every point you're going to spend log n time probably. You sweep a plane, you maintain all the intersections with the sweep line in order. When you get to a point, you do a binary search, that's all fine. But you also have to process all the intersections between the lines. Okay, so that's, if you just do a standard plane sweep, that's going to be n squared log n. Well, maybe doing it slightly differently, you can get n squared instead of n squared log n, but the big question is, can you do this faster than n squared? Okay, so using what I told you on day 1, maybe a little bit day 2 also, you should be able to do this in n times square root of n, or actually maybe in time n to the 1.5 plus epsilon. Okay, so how would you do this? Well, so this is n squared. So how you can do it is you say, okay, I take my point set and I compute a partition tree for the point set. Okay, then with a partition tree, or maybe a multi-level partition tree, but actually here that's not needed. With a partition tree, you can say, given a triangle, for instance, I can count how many points are inside a triangle. Okay, so you can view the line as a very thin triangle. So you can also count how many points are on the line. Right, and actually, if you think about it, you don't have to think about a line as a thin triangle. If you think about what the partition tree is, how it works. Okay, we had this simplicial partition. I have a query line of all of the okay. Now obviously, points from this triangle and from this one and from this one can never lie on this line, so I only have to search recursively in the triangles that are intersected by the line. So you do what you normally do in a partition tree, you go down to these two nodes and so on. Okay, so I construct a data structure the number of points on a query line, and then for each of my lines I do a query. Okay. As soon as one of the query reports number of points which is greater than 0, I answer yes. If all my queries give as answer 0, no points on the line, then I answer no. Okay, so what's the running time? Well, the data structure, well, actually you can construct it in even in n log n time if you want. So something like n log n or n to the 1 plus epsilon. And then here I do n queries. And each query is going to take me roughly square root of n time. So I get n times this is n to the 3 over 2 plus epsilon. Okay, so a lot faster than n squared. But the question is, can we do even better than this? So what happens if we use a cutting tree? Well, now this is pretty nice, right? Because here I get n queries times log n. But now constructing the cutting tree is going to take a lot of time because it uses n squared space, so we're going to also need n squared time to construct it. So it's actually worse than this, right? Step 2 is a lot faster, but step 1 is a lot slower. So the question is, can I maybe, but here for the partition tree, this is only linear roughly, so I'm allowed to spend a little bit more time than this to get this down. And in the end what I would like is that maybe this is exactly the same as this, that you really get something balanced. So what we're going to do now is to try to see if we can somehow modify our partition tree so that the space and also the pre-processing time will be a little bit higher, but the query time is going to be lower. Okay, and then by having a little bit larger pre-processing time but lower time here, hopefully we get a better bounce in total. Okay, so that's what we'll try to do. So the partition tree, well, you should know by now, it's we have the simplistic partition. For each triangle I have a subtree, and this subtree is the root of a recursively defined partition tree. Okay, so one way to think about it is think about the query algorithm. Okay, it's going to start at the root, going to a number of subtrees, going to more nodes, and so on. Okay, so here let's do something here and so on. So maybe I always go here, maybe I go here, and then in this one maybe I go here, here, and here, and well, for this one, oops, maybe also visit a few nodes. So I'm spending more and more time, and my goal was to get smaller query time. So the idea is basically, okay, I'm going down in this tree, but at some point if I want to have smaller query time, I'm visiting too many nodes. So then, let's say that by now I have visited, I already spent a lot of query time, and now I want to not continue in this way. Then this subtree here, for instance, okay, if I make it what we do usually, it's a recursively defined partition tree, then again here I'm going to look at the number of nodes. But now let me make this into a cutting tree. Okay, so somewhere, let's say in the middle of this tree, instead of saying, okay, I have this point set and I store it in a recursively defined partition tree, I say no, now I don't have too much time anymore for my queries, so instead I'm going to store it in a cutting tree. Okay, so that's so essentially, intuitively, when you say, well, when we have spent too much time for a query, we switch to a different data structure that is faster. And so, well, of course, if you say when we have spent too much time for the query, well, when we construct a tree, we don't know about the queries yet. So we have to, the decision whether we switch to a different structure cannot be based on the query. So instead I say, okay, if the number of points is small enough, so when I'm at a certain level in the tree, then I switch to a different solution, you could say. Okay, so here is my trade-off tree, you could say. It's defined the same way as before. Okay, have a set of endpoints. Compute a simplicial partition for the points. For each triangle you have a child. Recursively build a partition tree for that one, and so on. But in this recursive call, you say, okay, when the number of points is equal to some m, smaller than n, right, then I'm actually going to make this structure into a cutting tree. Okay, so what do I have to do? I get, let's say that happens here at this node. So for this guy I have a simplicial partition. Okay, each of these things has some points in it. Okay. And when I'm building the tree, okay, for instance, for this triangle here, well, maybe that corresponds to this node here. Okay, so when the number of points is at most m, well, then what I have to do, I have to take these points, I have to go to dual space. So I take my points and I make them into lines in dual space, and then I construct a cutting tree in dual space. Okay, and if the number of points would be bigger than m, I simply continue with my partition tree. So a different way to think about it is that my tree, now the highest levels are simply going to behave as partition trees, but at some point, let's say at this level, when the number of points is m, then these things are going to be cutting trees in dual space.
Okay. What is the number of cutting trees? You just have one triangle in partition tree, and then in the dual space we make a cutting tree, just one cutting tree for that specific triangle. Yeah.
Yeah. So here, let's say in this picture, then I would have this corresponds to this triangle, and there will be a cutting tree for this one. But also this, which corresponds to this triangle, there will be a cutting tree for that one. So here, all of these things are cutting trees. Yeah? So if I take a large m, what does it mean? Well, I'm going to switch from partition trees to cutting trees when the number of points is m. So if I have a large m, then I switch earlier. Right? And the earlier I switch, the faster the query time will be. So what happens if I take m equals n? What happens in that case? Yeah, I immediately start with the cutting tree and that's it. So I just have a cutting tree. If I take m equals 1, I have a partition tree. No cutting trees. But then I can play with this parameter m to see at which level you switch from partition tree to cutting tree. Okay, so this is the idea. Now let's see what happens to the query time, okay, and the amount of storage. So I'm going to write a recurrence for the query time. So let me first, this is the old recurrence that we had. Okay, before we did this other thing. So if you're at the leaf, it's constant time. Otherwise, well, check all of the triangles in my simplicial partition. On square root of r of them, I have two recurs. Okay? So now, what happens is that at the top level, I still have this recurrence. But when n equals m, I have a cutting tree, and what's the query time? Log n. Right? So essentially, now the base case of my recurrence is that when n equals, or is at most m, then I don't do my recursion anymore, but I say, okay, now I have a cutting tree. And I know that for a cutting tree, the query time is log n. Okay, so, and indeed you can see that when I pick m equals 1, I have my old recurrence back. So I get, because I simply had a partition tree. When I pick m equals n, then this whole thing disappears and I simply have log n. So the question is, what is the solution to this recurrence?
What must be log n instead of it?
Yes, yeah. You're right. It doesn't matter for the bound, but you're right. It's yeah. So my claim is that this is the solution. Okay, so you see I have my old n to the 1/2 plus epsilon, but it's divided by square root of m, meaning that the larger m, the smaller it will be. Okay, and what you also see that when m equals 1, okay, we just had our partition tree, then indeed the bound is simply n to the 1/2 plus epsilon. When m is n, it's maybe not quite what it should be, because when m equals n, okay, and I have n to the power epsilon, and it should be log n. Okay, so, but I didn't want to write, otherwise the bound becomes if this then that, and n to the power epsilon is definitely correct, right, because it's bigger than log n. And I mean, basically, if you take m equals n, I mean, you're not going to use such a trade-off, so you shouldn't use this theorem. So I claim that this is the solution. Of course, if I want to prove this using induction, I again have to get rid of the big O notation and write constants here. So let's say Qn is C times log n by the time when n is so small that that's equal to m. And otherwise, I have that recurrence. And, well, it's not so difficult to go through the computation. So here, in the base case, you get, well, I know it's C times log n. Well, log n is smaller than n to the epsilon. Here, n equals m. So I can multiply by n divided by m. And then what you get here is n to the 1/2 plus epsilon divided by m to the 1/2. So the more interesting case is the other one. Okay. For this term, I'm going to plug in my induction hypothesis. So you see the same thing, except that here, well, my induction hypothesis says that this is at most d times this quantity. But the n here is now this number. So I get 2n divided by r, 1/2 plus epsilon, divided by m to the 1/2. And then rearranging a little bit, this is the same. I get my c here, I have square root of r, but here I have divided by r to the 1/2 plus epsilon. So this r to the 1/2, since I divide, cancels out with this root r, and I'm left with r to the epsilon, so that's here. I also have a term 2 to the 1/2 plus epsilon, but since I write at most and I was a little bit lazy, I just write 2 here. And then I'm left with this term here. And similarly to before, what I did on Blackboard, if I choose r large enough, such that this thing here, let's say, is 4 times c, then this would be 1/2, and I want to prove 1 times this, so I have a little bit room to play with and to cancel out this term. Okay, so this is, but I don't know, solving the recurrence is not very interesting, so. Okay, so indeed the query time when m gets larger, the query time gets smaller, right? So it essentially goes down from square root of n to, well, log n, or the way I've written it here, n to the power epsilon. So what happens to the storage? So when m becomes larger, what happens to the storage? Larger or smaller? Larger. Right, so let's see how much larger it gets. So how can we analyze it? Well, the complicated way is to write another recurrence. Right, I had my old recurrence, but now the base case is not when n equals 1, but when n equals m, and then I have this bound. But actually, there's an easier way to look at it. If we just think about that picture, okay, the top part is a partition tree. How much storage does a partition tree use? Linear. Okay, so the top part is linear, so we don't have to worry about the top part. For the bottom parts, how many of these bottom parts do I have? Well, each of them has m points, so I have n divided by m of these cutting trees here. Okay, each of these cutting trees, well, I have n equals m points at that point, so it's n to the power 2 plus epsilon storage for each of these things. Okay, so if I multiply, this is the number of these cutting trees, each one takes this amount of storage, so I simply get n times m to the 1 plus epsilon. And then indeed, when n equals m, this is n to the 2 plus epsilon, because you just have a single cutting tree on the whole point set, and when m equals 1, you simply get linear. Okay, so above there you see the way we derived it. It's usually written in a slightly different way. Namely, instead of saying you have, well, the query time and amount of storage you see there, you say, well, if I want to have storage S, where S is between n and n squared, then the query time will be n to the 1 plus epsilon divided by square root of S. Okay, so that's exactly the same bound, because I say I take S equals n times m. Okay, then indeed I have, well, S to the 1 plus epsilon storage. So what's the query time? Well, that was n 1/2 plus epsilon divided by m to the 1/2 is, well, m equals S divided by n. So I get divided by S over n to the 1/2 is n to the 1 plus epsilon divided by S to the 1/2. Okay, so this is not a different result, it's just written in a different way. Okay. Hope this is clear so far. So remember why we wanted to do this? Well, we wanted to solve Hopcroft problem in a faster way. I forgot to mention, you can also do this in d-dimensional space exactly in the same way. Start with a partition tree and then switch to a cutting tree. And now you can vary the storage between n and n to the power d. And the query time will be, well, the same, except that here you divide by S to the 1 over d. If you have multi-level structures, it also, all of this works. Okay, so if you have a 3-level partition tree, you can also have a trade-off for the 3-level tree with the same time bounds. Okay, back to this problem. So, same algorithm as before. Construct, well, now I'm going to construct such a trade-off structure on my set of points. Then I'm going to do a query with each of my lines, and if one of them says yes, then I answer, or a count greater than 0, then I answer yes, and otherwise no. Okay, so what's the total time? Well, I used this much storage, and I didn't explain, but you can also actually construct it in that much time. Okay, so constructing the data structure takes basically S time, well, S to the 1 plus epsilon. The queries now, well, I take n queries, to n queries. Each of them took n to the 1 plus epsilon divided by S to the power 1/2. Okay, so the total time is simply this plus this, which is what is written here. So how do I want to choose my value of S? Well, exactly, right? I want, if I start with S equals n, that's what we did before, only use the partition tree. Then here I have n to the 1 plus epsilon, and here I was getting n to the 3/2 plus epsilon. Okay, so now I'm going to make S a little bit bigger, and this is going to get a little bit smaller, and then at some point they are exactly the same, and that's what I want, because if I make S even larger, well, at that point, at that point this would get the over. So if I make S larger, this becomes larger, this becomes smaller. When they're equal, I should stop, because otherwise this gets even larger. So So what I want to do is I want to set S should be equal to n squared divided by square root of S. I have these epsilons on both sides, which I'm ignoring now. So what does it mean? It means S to the 3/2 should be n squared. So S equals n to the 4/3. Okay, so by picking S equals n to the 4/3, I get, well, here I get n to the 4/3, so n to the 4/3 plus epsilon. And of course this term I don't have to compute it because I know it's going to be the same as this one. Okay, so I guess probably a number of you, if you've read a number of papers in computational geometry, every now and then you see this n to the 4/3 coming up. And that's always because of this trade-off between that you can get for this kind of data structures. And, well, actually, for this particular problem, you don't really need to first compute a data structure. You can sort of do it directly, but that uses essentially the same techniques. So it's doesn't matter. Okay, just a quick test. So if I want to do a Hopcroft problem in 3D, okay, so Hopcroft's problem in R3. So I have a set of points and I have a set of planes. Okay, and I want to check, is there any point on any of the planes? Okay, can do the same thing. Pre-process the points for counting queries and do a query with each of your planes. Okay, so let's say queries in R3. So as I said, exactly the same machinery works. So I have storage, I can get S to the 1 plus epsilon. Oops. And query is going to be, do you remember, it was n to the 1 plus epsilon divided by S to the power 1 over d, so 1 over 3 in this case, so S to the 1/3. Okay, so how do I pick my value of S? Okay, so I want S to be equal to and what else should I write? This was the pre-processing for Hopcroft problem, computing the data structure. Step 2 was do all these queries. Each query is taking this much time, but I have n of these queries. Okay, so here I get S to the 4/3 should be n squared, so S is going to be n to the 3/2. Okay, so Hopcroft problem in 3D, you can solve in n to the 3/2 plus epsilon. And again, these bounds are essentially tight. You can, instead of the epsilon, you can get log n, or sometimes there's even, you work very hard and you get something slightly smaller than log n, but basically the n to the 3/2 or the n to the 4/3, that's tight, and there are even lower bounds in certain models of computations that you cannot do it faster. Okay, I want to show you one more example of how you can use these trade-offs to do maybe a slightly more useful problem than this Hopcroft problem. And that's going to be to compute depth orders. So, do you know the painter's algorithm from computer graphics? Okay, so if you want to draw, well, let's say you have a set of triangles or some scene consisting of triangles, and you want to draw them on the screen. If you do it from back to front, each time drawing on top of the previous one, then in the end you have the correct view. Okay, so if you want to use this algorithm, then you have to compute this ordering. So that's what we're going to look at now. So for simplicity, let's just say that we have a set of line segments. Okay, I have a set of line segments, and I'm looking at the line segments from above, and I want to order them. Okay, so let's say a back to front ordering. Whenever something is below another segment, then this one should come before this one. Okay, so here I have something like, okay, this is behind this, so maybe if this is the first, then, well, this could be second, which is fine. This is above this one, but the number is 3, which is fine. This is higher than this one. 5 is more than 2, so that's fine. Okay, so a little bit of notation. I write this Si, well, let's say smaller than Sj if Si lies behind Sj. Okay, with behind I mean when I look at it, they actually intersect, and this one is lower. Okay, so it could be that this segment is much lower than this one, right, in z coordinate, but it's not behind, because when I project they don't interfere with each other, they don't intersect in the projection. Okay, so if I have this smaller than, then the problem I have is I have this set of segments and I want to compute an ordering which is consistent with this smaller than operation. Okay, so is this actually always possible? No, and why not?
You can make some segment in a circular order.
Exactly, right? In this relation there can be a cycle. So it can be that S1 is below S2. Did I do it correctly here? Okay, so this doesn't correspond to this. So here S1 is below S2, S2 is below S3, S3 is below S1. So this is a cycle, but what I wrote here, this should be the other way around. Okay, so you can have a cycle. Or did I do... yeah. Okay, S1 is below S2, S2 is below S3, S3 is below S1. Okay, yeah. Good. I was less sleepy last night than I think. Okay, so there can be cyclic overlap. So actually the depth order problem is maybe something like decide if there is cyclic overlap. If so, then simply say, okay, cyclic overlap. Otherwise, compute the depth order. Okay, and there's a very, so here's a simple way of doing it. Well, I'm going to construct this graph here. which has a node for every segment. Okay, and I'm going to put an arc from Si to Sj, so it's a directed graph, if Si is behind Sj. Okay, so here, for instance, S2 is behind S1, so I have an arc from S2 to S1. Okay, and apparently S5 is behind S4. Let's see, S5 is behind S4. Okay, so it's a very simple way of doing this would be construct this graph. Okay, how do you construct a graph? Well, for instance, project all these segments, compute all the intersections, and then for every intersection, well, depending on which one is higher, you add an arc in the graph going this way or going the other way. So this is very simple. For each pair that intersect, well, check if Si is below or above Sj and add the corresponding edge. Okay, and now a depth order is simply the same as a topological order on this graph. Right, the depth order was an order that is consistent with this relation, and this graph, well, encodes this relation, so an order on this graph, a topological order on the graph, is the same as a depth order, so you just run topological sorting. Okay, I guess all of you in one of your algorithms classes have seen that you can do topological sort by depth first search in linear time in the size of the graph. So that's easy, and then you either report that there's a cycle, or you get a topological ordering, and that's your depth order. Okay, so it seems like a kind of boring problem. So what's the running time of this?
N squared.
Right, in the worst case, n squared, because if you have bad luck, all these segments intersect each other and you get n squared intersections, and then, well, computing the intersections will take you n squared time, and actually the topological sort, you also have a graph with n squared edges, so it's also n squared. So the question is, can we do better? Okay, and well, the answer is yes, and it's going to be using some data structures similar to Hopcroft problem, except it's going to be actually somewhat more interesting in this case. So the algorithm is kind of nice, I think. So let me show you how to do it. So the idea is the following. I'm going to pick an arbitrary segment, let's say S1. Okay? Now I'm going to find and maybe just think about the case where there's no cyclic overlap. Right? It's not so hard to see when how the algorithm is going to detect when there's overlap, but it's maybe a little bit confusing if you think about this at the same time. So simply, let's say there's no cyclic overlap. Okay, so what the algorithm is going to do is pick this segment here, and now I'm going to, the other segments, I want to partition into 3 types of segments. Okay, and think about this graph. So I've all the segments or nodes in the graph which I can reach from this node. Okay, I have all the segments that can reach this one, and then I have some other ones like here. So from S1 I cannot go to one of the green nodes, and from the green nodes I cannot go to S1 either. Okay, so 3 categories. And note that these are different categories, because it cannot be that a node is both red and blue, because then you have a cycle, right? Then apparently I can reach this node, but the node can also reach this, so you would have a cycle. So since we assume that we don't have cycles, I just have these three classes. Okay, now what I'm going to do is find these three sets, sort them recursively, and now I claim that the correct order is first all the blue ones, then all the green ones, then S1, and then all the red ones. Okay. So if you, why is it correct? Well, you can prove it by contradiction. Let's say that this is not correct. That means that I would have, let's say in my graph, I would have an arrow going maybe from here to here. Well, I cannot have an arrow from a green to a blue, because if I have an arrow from a green to a blue, the blue can reach S1, so then the green could also reach S1, so then this green guy would be blue. Okay, so I cannot have an arrow going back like this. Well, also from S1, you cannot have an arrow here, because this is defined as the things that you cannot reach. You cannot have an arrow here, because then you would get a cycle and so on. So if you think about it, then indeed this is the correct order. Okay, so yes?
Step 2, you sort them by which property of the...
Okay, so here I mean, you can, maybe I should have written compute a depth order. Okay, so this is an algorithm that sorts according to this funny relation, and that's the same thing here. Yes, thank you. So this is the general idea, but this step here, of course, I want to do that without computing this whole graph, right? Because the whole point was that this whole graph could have n squared edges. So I don't want to compute this graph and then define these sets, because if I have the graph, I can just sort topologically. So somehow I want to compute these sets without computing this graph. And we're going to do that using a clever data structure to help us. So the data structure is going to do the following. You have a set of segments in three-dimensional space. Okay. And the query is, you get a query segment, the red one, and the data structure is going to report a segment such that the query is behind that segment. Okay, so here, which ones could it report? Well, S1 or S2. Right? It should not report S3, because S3 is behind, and I want something that is actually in front of S. Okay, so it should be able to answer this query, and I want the data structure to be dynamic, so I want to be able to insert and remove segments. Okay. Actually, I will also need a second data structure where this is the other way around, but that will be clear. Okay, so suppose I have this data structure, and actually using our partition trees and our trade-offs and actually some other more complicated things, you can get a data structure that has n to the 1/3 query time, but also n to the 1/3 time for insertions and deletions. Right, so it's going to use n to the power 4/3 storage, and then, well, this is the time for queries, and you get the same time for insertions, deletions. So let's just assume that we have this data structure, Now how can we use it to compute these red, blue and green sets? Okay. By the way, I don't think you get your extra time today. So this is the data structure. Now I want to find, let's just think about finding the red set. Okay? I have my S1. Well, if I do a query with S1, I get one of the segments which is above it. Right? So I get for instance this node. Okay, and then what I'm going to do then is I'm going to remove that one from the data structure and do another query with S1. Okay, I find this, remove it from the data structure, do another query with S1, and I find, oh, there's nothing left. Now I do a query with that red guy. Okay, I find, well, two queries, first that one, then that one. Okay, then I find there's nothing else. I do queries with the three other ones. The answer is nil, and I'm done. Okay, so here's the algorithm. I'm going to build this data structure on S. Well, let me already remove S1. Okay, I'm going to have a queue which contains all the segments where I still want to check if there's something above. Okay, so initially I only have S1 in my queue, and then as long as the queue is not empty, I say dequeue a segment, then do lots of queries until there's nothing above that segment anymore. So you do a query, you find something, remove it, do a query, find something, remove it, do a query. Oh, the answer is nil, so that's it. Okay? Everything you find, you put into your set S+, so that's one of your red nodes, and you put all the ones that you find into the queue, and then later you will start searching from them. Okay, so so this way, if, oops, there's a typo here. My queries take n to the 1/3 plus epsilon time each, and the number of queries I do is simply the number of things that I find. Well, not quite, because for each one of them you do one extra query where you find, hey, there's nothing left, but in order of magnitude you get this. Okay, so this is pretty nice. So what's the running time now? Well, let's say that n plus is the number of red nodes, n minus the number of blue nodes, and n0 the number of green nodes. So in step 1, for each of the red nodes, to find a red set, it takes n plus times n to the 1/3. For each of the blue nodes, same thing. This plus this, actually plus n0, is at most n minus 1, right? That's all the segments except for S1. So this is n to the 4/3. So the running time is, well, n to the 4/3 plus these recursive calls. Okay, so if this is nicely balanced, like each of these are n over 3 or something like that, then I would get n to the 4/3. But the problem is, it could be that one of these sets is very large. So let's say this is empty, and here I get t n minus 1. and then it's going to be really slow. It's going to be more than quadratic, perhaps. So let me just briefly mention, discuss the very nice trick you can use to get around this problem. So instead of computing red, blue, and green, I'm going to say, okay, look at the red and the blue. I'm only going to find the smallest of these two sets. Okay, so here you see, compute the smallest of the two sets, S plus and S minus. Well, now my S star is going to be the rest. So if the smallest is S minus, then my S star is going to be S plus and S zero. Right, and I cannot distinguish between them because I only found S minus. Okay, so the question is, how do you find the smallest of the two sets? Because before finding the sets, you don't know which one is the smallest. So there's a very nice trick if you use these data structures where you say, okay, let me first find something here, then something here, then something here, then something here, until for one of the two I'm stuck, and then I stop. Okay, so I first try to find a red node. Okay, I try to find a blue node. Oh, this should be blue. A blue node. Try to find a red node. Try to find a blue node. Try to find a red node. Oh, now I cannot find any blue nodes anymore, so I stop. And I say, okay, this is my blue set, S minus. I already had something for S plus, but there could be more. So all the other ones I take together in my S star. And then I recursively sort these things. And, well, if you think about it, the ordering that you get here is still the correct ordering.
Without this plus, how can you find this? Without this plus, how can you find this zero?
Without
this plus. This plus.
Without S plus, in the recursive call, or what do you mean without S plus?
You find just one of these two.
Yes. Yeah.
But the zero was the remaining.
Yeah. So I'm going to put. So I find, let's say, S minus. Then all the rest, which could be S plus or the remaining ones, I'm all going to put them all together and say, well, these are my remaining ones, and I don't know whether it's S plus or S zero. Right, so here, this S star actually is the union of these two. And I sort that one recursively and that one recursively. And then again, if you think about it, this is the right order. So now what's the running time? Well, now I did this tandem search, so I found S minus. The number of queries is this. Well, I'm actually doing 2 times this number of queries because I also did the query on the other set, but that's just this constant which disappears. So after this much time, I have found S minus. So the recurrence is going to be this plus, these two should be taken together, sorry, plus T minus plus, well, let me write, so I get Tn is O of this plus T and minus plus T and plus and 0. Okay? And the crucial thing is that this n minus is at most n over 2. And that means it could still be very unbalanced, right? Because S minus could be really small, and then this could be really large. But the good thing is, if n minus is really small, then here I spend very little time. Right? Because then this is very small, so I spend very little time. And a different way of looking at it is that here, for each of the segments in S minus, I spend n to the 1/3 time. Okay? So how often do I spend n to the 1/3 time for a segment? Okay, it starts in the big set, and then it goes to a set S minus, which is only size n over 2. So that can happen only log n times. So then for each segment you have something like n to the 1/3 times log n, and the log n is basically disappears because of the epsilon, so I get n to the 4/3. Okay, so well, I think this algorithm had some nice tricks with this tandem search and so on. And again, you can only do this if you have all these data structures available. So, well, if you know, let's say, your data structure theory, and you have some clever ideas, then, for instance, for this depth order problem, you get n to the 4/3. Okay, that's it. So the next 2 days are going to be something completely different. So you can forget all I told you these 3 days, and we'll start fresh. Well, I don't know how fresh you will be after all these lectures and Joachim's talk and so on, but so we'll do something else then. So are there any questions? No? Okay, then let's have tea or something else and